In this segment, we're going to talk about how to get beautiful renders. We're going to talk about surface tessellation so that your NURB objects are smooth. We're going to talk about anti-aliasing and how to adjust the quality and see the effect of the quality. And we're going to talk about field rendering. This is the scene that we're going to use to do our tests. Note the jagged edges. Note that the object isn't tessellated correctly. And it also has a nice color gradation from the inside to the outside, so we'll be able to see artifacts and shading problems. First things first, let's set up its render output file name and call it the quality test. And for right now, we only need to do one frame. Later on, we're going to adjust the anti-aliasing level. But for right now, we're going to take a look at what we can do with adaptive surface subdivision. What we want to do is we want to have the mental ray determine how much it needs to tessellate those NURBs at render time so that we're sure that they're very smooth. Now right now, and by default, they have a parametric 3x3 tessellation, which means that each NURB span is subdivided recursively 3 times. We're going to go with fine, and we're going to go with view dependent. What this means is that now the mental ray is going to look at how long each NURB span is in screen space and decide how to tessellate it to get down to our limit. In this case, we're going to say anything under 3 pixels should be subdivided recursively. And we're also going to increase the max subdivision recursion limit. There, now we can see it really smooth up the edges. Without, that's without view dependent, 3 soft mesh units, and then with view dependent, which means calculated in screen space and make sure that each span is less than 3 pixels long. Beautiful and round. Next step, let's talk about optimizing our anti-aliasing levels. Now we have a minimum and a maximum level. Areas where there's very little change from one sample to another, we don't want to refine recursively very much. In other words, if it's white and then the next pixel is white, there's no point in casting arrays in between those 2 pixels. However, if one pixel is white and the other one is green, then we know we've gotten close to the edge of one of our objects and we should do some more work on it. Now we're going to be able to tell this and get a better example of what we want to do by turning on the diagnostic node. In the diagnostic node, we're going to get little white dots where the samples go. So we'll be able to see a distribution of samples in our scene. In the black areas, there's not very many samples, and in the white areas, there's a lot of samples. So here we can say that we want to have the minimum level set to be quite low so that mental ray doesn't spend unneeded time rendering samples that aren't very different from one another, and the maximum level a little higher. However, even more important than that is the threshold. In other words, how different do 2 samples have to be before they're subdivided recursively? This is the most important setting in this dialog. By default, it's 0.2, which means that the samples can be 20% different before they're subdivided recursively. That's really too high. If we set it down to 0.05, we can see that we're getting a lot more samples in the interior of the object where they're necessary, and quite a bit fewer outside of the object. We are picking up a whole bunch of samples for the reflections in the walls too. So we can see there's a lot of detail that we were missing in the previous render, and we just didn't even know we were missing it. Okay, now we might want to increase the actual maximum level from 1 to 2, for instance, for final production work. But even at a maximum subdivision level of 1, which means 4 rays per pixel, we're getting quite smooth results. Finally, we'll set up the filtering. The box filter is not particularly effective. It means that each sample is weighted equally. So in other words, if we cast 4 rays at a pixel, each one of the 4 corners is going to count an equal amount. Gaussian is going to do a distribution where the samples that are closest to the center of the pixel, or wherever the sample is calculated from, count more. But there's some new options. Mitchell and Lankosh are even more sophisticated filters, and they have a tendency to accentuate edges, kind of like an unsharp mask, as well as smooth the samples beautifully. I would recommend a Mitchell or Lankosh with a fairly high number, 3 or 4 or 5 or 6. Next, let's look at some anti-aliasing. So we'll turn up the number of frames we're going to render to 100. And look at some field rendering. Field rendering means we're going to render a separate frame to fit into the odd lines on your television and your even lines on the television. This is accomplished by actually rendering pretty much 2 separate frames. However, each frame only has to have half the vertical resolution. So we'll turn on Enable Field. Here in the United States, we want the bottom first, which is otherwise known as odd field dominance. That means that line 1, then line 3, then line 5 get done, and then the even ones, 2, 4, 6, and 8. We also want XSI to interleave the frames, which is to put them back together once it's done. Like I mentioned, there's no sense in rendering twice as many lines, since we only need half to go in each set of fields. So we'll take the resolution and we'll say half. Now in this version, which is 3.5, there's something of an unfortunate side effect of this, which is that every time we do a render, it's going to cut the resolution in half. So it means that if we did a render twice, we'd end up with smaller and smaller and smaller frames. So we'll have to go back and reset the resolution periodically to make sure that this works correctly. Here's the resolution. This is where we might want to change it later. It's going to cut down the resolution in Y to be exactly half of 486, so 243. But if it goes below that, we're going to know that it's screwed up. There we go, 243. But it also cut the X resolution in half, which was incorrect. So let's change that back. And this time we'll turn off maintain picture ratio and try it again. Now we get what we'd expect, which is a stretched image. We'll just time lapse that as it renders. Now we're going to get twice as many frames. So if we were previously going to render 100 frames, we're actually going to render 200 frames now. One set of frames for the odd lines and one set of frames for the even lines. Okay, that was pretty quick. Now let's load those into the flipbook and see what we get. If you look carefully, you'll be able to see that there are 2 images superimposed on top of one another. See the ghost image? That's because one image is actually going to be sent into a separate fields on your television 1/60th of a second after the first set of fields. Now, it looks dumb on a TV monitor, or on a computer monitor, but it'll look great on TV. Because we're going to render, or we did render, and we're going to show effectively twice as many frames per second, the motion's going to be much, much smoother. In this section, we learned how to adjust the adaptive tessellation for NURBS objects. We adjusted the anti-aliasing and the anti-aliasing threshold.